Hello, today we're going to work on lesson 9.4, continuing with our confidence interval chapter. But this section is going to be mainly focused on what is the appropriate sample size for different confidence intervals. So go ahead and turn to page 213 in your course pack, and we'll get rolling. So, some basic reminders about confidence intervals and sampling. We use confidence intervals to turn sample data into predictions about the entire population, called the inferential statistics. That's what we're doing in actually chapters 9, 10, and 11. So our first example says, there have been 45 presidents of the US. Their mean height is 70.87 inches with a standard deviation of 2.8 inches. Explain why these data should not be used to construct a confidence interval for the mean heights of the presidents. Well, we have population data. So we cannot use it to predict further. And because we only have 45 in our population, we'd have to say that taking a very small number would still keep it independent and normal from all of our central limit theorem requirements. Example 2. On a Yahoo Answers board, a user wrote the following: the bigger the sample size, the more accurate the survey. Taking 1,000 people at random from an impossible million people who will vote is very, very inaccurate way of sampling. The ideal situation would be to call everyone in the whole US, and even then you would still not have everyone, because I'm sure there are some people without a phone that would still vote. So, explain what is correct and incorrect. So let's underline what is correct in this statement. So, it is ideal to call everyone in the whole US. That is correct. But it's not possible, right? And it's also correct that even if you do call everyone, there's still going to be some people that are going to vote that don't have a phone. So those are both true statements. And they're all the more reason that just because you're getting a hold of everyone doesn't give you all the information that you need. Because there's some people that you couldn't reach even with the phone. Part of it that's incorrect is the bigger the sample size, the more accurate the survey. That's not always true. Okay, that's incorrect. Bigger isn't better. Isn't necessarily bigger. Or isn't necessarily better, I should say. Taking 1,000 people at random from a possible million people who will vote is very inaccurate. That's not necessarily true. Maybe 1,000 is enough if it's a good random sample. So that's what we're going to study today. So this gray box down here at the bottom is a very important box that deserves to have a sticky note for your note sheet. Quantity versus quality. So when taking a statistical sample, we need to know the minimum sample required to obtain the precision, which is our margin of error, very important, and the confidence, which is our C level, that we desire. We will have formulas for these in this section, but never forget that the quality of a sample is always more important than the quantity. So you can have a very big sample, but if it's not giving you quality sample, then it's worthless. Okay, so back in 1.5, we said results from unscientific polls are worthless, but used all the times. Unfortunately, for a 7-minute radio article, you can check it out right here, but it is very important to have quality over quantity. So the first formula that we're going to look at is the sample size formula for estimating the population proportion. And so we need to know the confidence level that we're trying to create. And sometimes we're going to have a prior estimate of information for maybe a similar poll that was taken a year or sometime earlier. And then sometimes we have no prior estimate. So we need to know which one we're dealing with because you can see that the, the formulas are slightly different. So for this one with the prior estimate, we need that prior estimate P hat. And then we're going to use Q. Q is 1 minus P, the complement. Then we need to find our critical value for the confidence level that we're looking for. We're going to divide that by our error. Error is going to be a decimal because we're dealing with proportions or percents, and make sure that that ratio is squared. If we have no prior estimate, it's similar but different in a way because instead of having P hat and Q hat, we are just going to use the worst case scenario that maybe P is 0.5. So P times Q would end up being 0.25. So we're going to use that when we don't have a prior estimate. And then our ratio is still the same with the critical value divided by the error squared. The other thing that's very important, again, this gray entire box deserves a sticky note. Now these formulas are in your gold sheets, but just it's really important to make a note that whenever you're doing sample size, you always have to round up to make sure that you have enough in your sample. Rounding up to the nearest whole integer, and you'll see how I do that today. So example 3 says, suppose a researcher wants to know what proportion of US college students do not have health insurance. How many college students would the researcher need to poll if the researcher wants 95% confidence within a 3% margin of error? Note, these are the most typically used by news organizations. So 95% confidence means that alpha is 1 minus 0.95 or 0.05. And so alpha divided by 2 is 0.05 divided by 2 or 0.025. So we need Z of 0.025. We're going to need that in a minute. And then also they want us to show all the parts in formula substitution and then we'll calculate it. So let's just fill this in and then we're going to go to StatCrunch and the TID4 to show our work. So in our formula here, they told us that we need to know let's see, we have no prior estimate here, so we're going to use 0.25 right here. And then our critical value is going to go in the numerator, which we're going to find just a moment in StatCrunch. And our error is equal to 3% margin of error. And so that is going to go as a decimal right here. So let's go check it out. Okay, so this one right here. So we are looking for a standard, and we're looking for the mean is at 0 and 1 because we're talking about z-scores. And we want to know 0.25 here, 0.25. And we're going to find the z-score that goes with that. And I used a normal calculator and I didn't, oopsie. I need to go back there. I need to put in, we know the area is 0.25. That's what I need. And we find out that I put 0.25, 0.025. There we go. So there is the correct Z value that goes with that. Our critical Z is 1.96. And so with our calculator or TI-84 calculator, I must have gotten rid of that. TI-84, we need our TI-84 app open here. We're going to put in our formula that we looked at. Okay. So here we are. So we're going to say 0.25 and then a parenthesis, alpha y equals, and we have 1.96 in the numerator. Our error is 0.03. There we go. And there is our sample size, 1067.1, and we always round that up to the next integer of 1068. And you'll see it on my paper here momentarily. So we rounded 1067.1 up to 1068. So next it says the researcher wants 95% confidence still, but within a 4% margin of error. So we're increasing our margin of error that we're willing to have. So we have 0.25, 1.96 stays the same. Our margin of error is different. And then we have squared. So the only thing that's changing is we're getting a bigger value in our denominator. So we're dividing by something bigger and we're allowing more tolerance. So let's see what happens to the value. So you put that in your calculator and I got 60.25 and we're gonna round that up to 601. So you can see that as our margin of error went up, our sample size went down from 1068 to 601. Part C says, a 2016 study found that 8.6% of US college students do not have health insurance. Now, how many people would the researcher need to survey to have a 95% confidence, so same confidence level, within a 3% margin of error? So we're comparing basically to part A, but this time we have a prior estimate. So we're going to be using this formula here. So N equals, we're using the P hat, Q hat, critical value over the error squared. Okay, so our P hat is 0.086 times 1 minus 0.086 times, our critical value is staying the same, 1.96. Our error is 0.03, and we're going to square that. And that comes out to be 335.5, but of course we're going to round that to 336. So we can make a couple of connections here. Down here in the gray box, this you are definitely going to need to have on your note sheet. I would have a whole section on your note sheet for each chapter, because each chapter you're going to refer back to pieces in your gold packet, but you want to have the little nuances on your note sheet. And this is one of the nuances for section 9.4. Increasing your error, your margin of error, means that you're going to lower your sample size if all other items stay the same. And then having a prior estimate for P means, notice we went from the same confidence and same error, and all we did was have from A, no prior estimate, to C, prior estimate, and we only have like a third of the sample needed. So again, we're gonna lower our sample size. So likewise, that also means if you decrease your error, you're going to raise your sample size. Remember, they go increase and lower, they go opposite of each other. Again, if you don't have a prior estimate, you're going to have a bigger sample size. Okay, so this is all for estimating population proportion. So page 215, we are going to look at the sample size needed for estimating the population mean. And we only have one formula for this sample size. Again, we're going to be rounding up to the nearest integer. The other thing here is that our error, the error has units. Whereas with proportions, the error is just a percent that you turn into a decimal. But now, because we're talking about the mean and something quantitative, we're talking about units. So we have to make sure that we think about that when we're looking for the error. So example 4 says a medical researcher is interested in the average amount of time people in the US spend on the internet per week, assuming an estimated standard deviation of 6.2 hours. How large a sample should the researcher collect if they want to be 80% confident within 2 hours of the true average time spent? So within 2 hours means that that's our error. Okay, so our alpha is equal to 1 minus 0.8 or 0.2 because we are 80% confident. So alpha divided by 2 is 0.2 divided by 2 or 0.1. And you can either use the normal curve table in your yellow sheets, your inverse norm, or StatCrunch. And we find out that the z of 0.10 is 1.282. Giving you a hint, inverse norm does that for you. So our formula is going to be n. Our sample standard deviation is 6.2 hours. And our critical value we said is 1.282. And our error we said was 2, and we're going to square that. So when we put that into the calculator, everybody should be practicing this. Practice makes perfect. So when we practice this, we're going to say second and alpha. And we're going to have 6.2 times 1.282. In the denominator, we're going to have 2 hours. And we're going to have a right parenthesis here. And we're going to have a left parenthesis here. And then we need to go back over here and say square that. And there is our value. So we would only need a sample of 15.79, but again, that rounds up to 16. Okay, part B. Part B says we want to have a 98% confidence. Okay, so we're really increasing the confidence that we would like to have, and we're going to keep that within 2 hours of the true average. So our formula is going to stay the same. The only thing that's changing is our critical value. So our critical value, let's just go and check that out. Our critical value, inverse norm, is our alpha is 1 minus 0.98. So this time it's 0.02. Alpha divided by 2 is 0.02 divided by 2. So alpha divided by 2 is 0.01. So we're looking at an area of 0.01. And that comes out to be 2.326. So we can go up. We're using essentially the same formula as what I have highlighted right here and hit enter, and then we can just edit that, which is really nice to be able to do. And instead of 1.282, we have 2.326 and hit enter, and we can see that we now need a sample of rounded up 52 people. So we went from 16 to 52. Okay, so I'm going to show you all my paper just so everybody can see that here. So the new critical value was 2.326 because we had a much higher confidence from 80 to 98. And we over tripled the sample size that we're going to need for that too. So it says the researcher realizes there was an error and the standard deviation was actually 7.5 hours. So it's actually bigger. We're varying by the mean much more than we thought. Now, how many should they sample to be 98% confident and within 2 hours of the true average time spent? So this time our sample standard deviation has changed. Our error is the same. Same confidence, so we still have a critical value of 2.326. squared. So when we change just from the previous one, our standard deviation, our sample size goes up to 77. So that's a big increase. Increasing confidence level down here, a nuance. Increasing confidence level means you're going to have to increase your sample size. Increasing standard deviation means you're going to have to increase your sample size. Important things to remember. Okay, let's put it all together. So page 216 here says, a recent Huffington Post poll found that the pollsters are 95% confident the percentage of all U.S. adults that believe that the U.S. should take a global leadership role in trying to prevent climate change is somewhere between 57.8 and 64.2. What parameter is being estimated? Population P proportion, right? What is the confidence interval again given? Okay, they gave us it's 0.578 up to 0.642. Draw a graphic of the confidence interval. So there's 0.578 up to 0.642. What is the point estimate of the interval? So the point estimate should be right dead center in the middle, and we're going to find that by taking the upper plus the lower and dividing by 2. And make sure you add these two first before you divide by 2, because you would hate to make that, that error. And you could do that by putting them in parentheses, 0.578 plus 0.642 in parentheses, and then dividing by 2. And 0.61 should be your point estimate in the middle. What is the margin of error of the interval? Label it on the graph. So the margin of error is this space here. This is our margin of error, and it's the same amount as what's between here, right? Margin of error. And the margin of error can be found by taking the upper minus the lower and divided by 2. That's the same as the width. And the width down here is the upper minus the lower. That is the width. Or you can say 2 times your margin of error. That's always an option. And you can do that by saying 0.642 minus 0.578 and dividing by 2. And that comes out to be 0.032. What is the width of the interval? So the width is the upper minus the lower. .642 minus 0.578. And that's 0.064. You can see it's half of the margin of error. I'm sorry, double the margin of error. If the margin of error increased to 4.5%, what would happen to the width? It would also increase. It would increase to 9%. So a little note down here at the bottom, it says a formula for width, which we said is the upper minus the lower, or twice the margin of error. Also, a larger margin of error equates with a wider interval. So we need to make sure that we note that as well. Now we have two little examples for you to work through and make some connections here. So if you turn to page 217 in your book, in your course pack, it says, how are sample size and margin of error and width related? So we have three scenarios here where we give you the mean, the sample standard deviation, the sample size, the confidence level, and we're asking you to find the confidence interval for mean and the margin of error. And we know that the confidence interval for the mean is found in your calculator. You can always find this in your gold packet on page 266. The confidence interval formulas are here. So the confidence interval for a mean is the t-interval. Also, the formula sample size for confidence intervals are at the bottom of that same page. So what we're going to look at here is we're going to be using the t-interval in our calculator. And notice the similarities and differences here. The three scenarios, they all have the same mean. They all have the same sample standard deviation, but it looks like we're increasing our sample size and confidence level is the same, right? So we're going to make some connections between what's happening when we change our sample size. So let's go to our graphing calculator for a moment. And we're going to clear this all out, and we're going to go to stat, and we're going to arrow over to test, and we're going to go down to the t-interval. And we're going to just keep changing this. We don't have data. We're going to go over to statistics and hit enter. So the mean, we're going to keep working with similar over and over, is 350, standard deviation of 100. This time our sample size is 50, and our confidence is 0.95. So we're going to hit enter, and it gives us a confidence interval of 321.58. 378.42. So let's go ahead and do the other confidence intervals, and then we'll change to our course pack page and we can calculate the margin of error together. So let's go back to stat and over to test and down to t-interval and hit enter. And the good thing is everything is there. We just have to change our sample size. Now we're going to say, what about if our sample size is 150? What does that do for us? And there is 333.87 and 366.13. Excellent. And one last time. Down to t-interval. And this time our sample size is at 250. And there it is. So you know what? That doesn't seem right. What did I have last time? It looks like 337. Let's just take a look at this here. So this is our third confidence interval here, 337.54 and 362.46. And this is for the sample size of 250. So let's go ahead and share. Let's go back to sharing our screen here with our main page and the course pack. So here are the three confidence intervals that we just received for sample sizes of 50, 150, and 250. And our margin of error is by taking the upper minus the lower and dividing by 2. And for this one, we get 28.42. And the second one, we get 16.13. And the third one, we get 12.46. Now, we're going to try to make some connections here with this. So it says, how does changing sample size affect a confidence interval or margin of error for mean? So let's just see, as our sample size goes up, it looks like our margin of error is going down. Margin of error is going down. And our interval is smaller. It's not as wide, right? This went up a little bit, and this went up a little bit more, and then this went down, and this went down, and it's just getting tighter and tighter. Okay, B says, consider the confidence interval formulas for mean and proportion. So this is the one we're going to use on this one. Why does the result from A make sense? So, because when n goes up, n is in our denominator, that means our denominator is increasing. And when our denominator of a fraction increases, the overall fraction value, right? What happens to that? Denominator gets bigger, the overall fraction gets smaller. Then when you're multiplying your critical t by some smaller number, right? That means your margin of error is going to decrease. Okay. So we have to make sure that we're making connections with that. The relationship between the sample size and confidence interval and margin of error. So as the sample size gets bigger, right? Sample size gets bigger, the margin of error goes down. So one goes up, the other one goes down. It's like a teeter-totter. Let's look at our second example. This time we're going to play around a little bit with changing some things, but we're going to do it with the proportions because it helps us look at creating the confidence intervals for proportions. And along the way, we're also going to look at changing. This time we have what is changing. It looks like it's our confidence level that's changing. So our p hat is found, let's remind ourselves, p hat is found by taking x divided by n. So 50 divided by 100 is 0.5 for each of these. And this time, the confidence interval formula that we're using is 1 prop z int because we're talking about proportions. So let's just write that down on our paper. 1 prop z int. And let's just go to that in our graphing calculator here. Let me share screen. And we're going to go to stat and over to tests. And we're going to go to 1 prop z int. So let's just go, that's letter A that we're looking for here. And we have x is equal to 50 out of n is 100. And our confidence level that we're going to start out with is 0.8 for 80%. And let's just calculate that. Okay, so we have 0.43592 and 0.56408. And let's run that again and see what we get. And this time we're going to run it for a confidence of 0.90, 90% confidence, and see what comes up. So now we have 0.41776 and 0.58224. And we'll share our screen here in just a minute so that we can make sure that we've got the same thing written on our paper. And lastly, we're going to look at a 95% confidence and see what happens here. So we have 0.402. And 0.598. And we're going to calculate our margin of error, and just remember that our margin of error here is calculated by taking our upper. So the first one is going to be 0.56408, subtracting our lower 0.43592, and then dividing that by 2. So our first margin of error should be 0.06408. And then we're going to look at the next one, and we're going to have 0.58224 minus 0.41776 divided by 2, and we're going to have 0.08224, and then 0.402 minus 0.598 divided by 2. We should have started with 0.598, right? Minus 0.402 divided by 2. We should still get the same. So 0.098. So let's just go back and share what we've got going on here. You can see that as we're increasing our confidence level, what happens there? Our margin of error is getting bigger. So this is opposite of what we just saw on the last one. So how can we see that in our formulas here? So we can see that as our confidence level goes up, what happens here? So what happens here is that our confidence goes up and our critical values also go up. And so that makes our margin of error go up. And those are important to note essentially down here, the relationship between confidence level and confidence interval, margin of error, and then standard deviation. So if confidence level goes up, margin of error goes up. And also, if the standard deviation goes up, our margin of error goes up as well, because standard deviation is in the numerator, and that's going to make your value of your margin of error go up as well. So this is really good stuff. So we'll see you back for chapter 10, where we officially start hypothesis testing. Pretty exciting. See you then.